Hi, this is Stephen Brower. In this video, we'll take a look at 2's complement, and then we'll look at the range for signed binary numbers. One of the early issues that they tried tackling in computers was how to represent a negative number. And so initially they were thinking if you had, let's just say 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, that the leftmost bit would indicate that it would be negative. And by the way, this is, let me put here, bad. I just want to explain why. That the leftmost would be the sign, and so let's say we're trying to represent a -5. Well, a -5 would be, in a sense, 5 with a 0 in the sign position. The issue is, let's say, and if we can, let's say we're talking about regular math, -5 plus 6 is 1. Well, if this was our -5 and we tried to add to it 6 as positive, if we went through and actually tried to do the addition, we would end up with, well, a negative value, because we'd still have this 1 in the leftmost position. So the bad part what I'm saying is bad, is that we can't do math with a number in this situation, meaning that the processor would have to do something different when dealing with negative numbers as opposed to positive numbers. So then the idea in terms of the 2's complement was to then represent that number in a way so that we can do math with it. And so the 2's complement, the process will be, you flip the bits, or I'm sorry, first put this way, represent the number that you're trying to do first as positive. So represent the positive number, then flip the bits, and then add 1. So if we were trying to represent -5, so to represent -5, the first thing we do is, let's represent 5. So if we're representing, and when you're doing this, you have to have, if you're talking about 8 bits, you have to show the 8 bits. That's very important, because if you only deal with where the 1 begins, you're going to throw things off. So 1, 2, 3, 4, 5, 6, 7, 8. So a 5 in binary in 8 bits would be this. So this is representing the 5. Remember, what we're trying to do is represent -5. So then we'll do the flip. And what the flip is, anywhere there's a 0, we make it a 1. Anywhere there's a 1, we make it a 0. It doesn't matter whether you go left to right or right to left, because you're just taking whatever is there and flipping in terms of the opposite. So there's the flip. And then we do the add 1. Add 1. So here, if I add 1, now I am going to go right to left here just to be safe. 0 and 1 is 1, and then everything else is just going to carry down. And so this here, this would be -5 in 2's complement. The leftmost position is still indicating whether something's positive or negative. So when we glance here and we see that there's a 1, we know that this is a negative number. Well, for giggles and grins, since over here I was trying to do the -5 plus 6, let's see what happens if we do that. So let's do the minus 5. Okay, so the 1, 1, 1, 1, 1, 0, 1, 1. And then let's add 6. And remember the 6 that's 6 in binary. So here's the negative 5 and 2's complement. Here's the 6. 1 and 0 is 1. 1 and 1 is 0. We carry the 1. 1, 0, and 1 is 0. We carry the 1. 1 and 1 is 0. We carry the 1. 1 and 1, 0. Carry the 1. 1 and 1 is 0. Carry the 1. 1 and 1 is 0. Carry the 1. 1 and 1 is 0. But when we're dealing with 8 bits, there's no 9th bit. So we don't go stick a 1 here. In terms of if we were doing this as a plain old binary math, yes, we would add 1 here. That would be the leftmost. But if we only have 8 bits, there's no 9th bit to stick that 1 into. Well, that's 1. So the negative 5 plus the 6 is 1. The other thing about the 2's complement, when you add, if we add 5 and negative 5, we should get 0. And so one of the things that, in a sense, we could do, so if this is our minus 5, so remember, this is minus 5. If we add to it 5, we should get 0. So our 5 was, that's this number up here, what we began with, 0, 0, 0, 0, 0, 1, 0, 1. Okay, this is a positive 5. So 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1, 0, 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 0, carry the 1. 0, carry the 1. 0, carry the 1. 0, and there is no carry. And so this is 0. So the negative 5, which was this number here, plus 5 gives us our 0. So the 2's complement, it's a form that we can put a negative number in where we still can do add. Now I'm jumping ahead to next week's lecture, but one of the things we're going to see next week is there actually is an assembly command called add. Well, add, it doesn't know whether it's adding positive or negative numbers. It's the same process. It starts from the right and it just, adds to finally come up with the number. It will set some flags based on what it has. What I'm getting at, and I'm doing a foreshadow for the future. So add and sub, they deal with both signed and unsigned. Later in Chapter 7, we're going to see multiplication and division. There's one command for unsigned multiplication, another command for signed multiplication. There's one command for unsigned division. There's another command for signed division. So this 2's complement works well with adding and subtracting, but when we get to multiplication and division, we're going to have to do something different. So when we get to Chapter 10 in Stallings, one of the things we'll take a look at is Booth's algorithm for multiplying signed numbers. Sorry, I just got a text from my doctor. No, everything's okay. Everything is okay. Oh, and by the way, the early processors didn't actually subtract. They actually would use the 2's complement and do an add. And what I mean is, suppose what we wanted to do is do 6 minus 5. Well, if it didn't have subtraction, what it would really do is say, well, let's do 6 and add negative 5. And so what it would do then is it would basically go through the 2's complement process, flip the bits and add 1 for the thing it wanted to subtract, and then it could go through and do the add. So some early processors, behind the scenes, they only had logic for just add. because then subtraction was just treated differently. Okay, I'm at 10 minutes, and let's see if I can do this part here in terms of the signed ranges. Now, let's take a look at 4 bits. And so if we're dealing with 4 bits and we're dealing with a signed number, and I want to talk about the largest. So the largest being, this would be the positive number. What's the largest positive number that we can represent? Well, the largest positive number, we have to have a 0 in the leftmost position, because if we have a 1 there, it's then considered negative. So the largest positive number that we can have, we'd have a 0 here, and then we would have 1 in each of these positions. So just a reminder, 2 to the 0, 2 to the 1, 2 to the 2, that's a 2, 2 to the 3, sorry, this is a 2. Okay, so this 111, which is 7, it's 2 to, start over, I'm sorry. I'm running out of time. I'm sure that's a 2. So 2 to the 3 minus 1, okay, which is 8 minus 1, in this case, which is 7. So when we're dealing with 4 bits, the largest positive would be 2 to the 3 minus 1. So if we're dealing with 8 bits, so again, if we were dealing with 8 bits, so if we're dealing with 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, and we want to leave the leftmost bit as being a 0, so then that would be 2 to the 7 minus 1, and 2 to the 7 is 128, so 128 minus 1 is 127. And so in terms of the largest positive that we can have with 8 bits, if we're dealing with signed 8-bit numbers, then 127 is the largest that we can have. I'm not going to do justice to the other side, meaning the smallest positive. But first, let's take a look at 4 bits. If we have as a 4-bit number this, and this here, this 1 indicates that it is a negative, well, let's figure out what this is. So if this is our negative number, let's use the 2's complement process on it to see what it's a negative number of, meaning a negative number of a positive. And what I want to get at, if I come back here for a second, is suppose we were given this as our starting number, and we wanted to know, well, what is it? If we took that, we flipped the bits, and we added 1, we would then come back to what our 5 was. So if I go through the process here, if I do the flip first, so 0, 1, 1, 1, and then I do the add 1, so plus 1, 1 and 1 is 0, carry the 1, 1 and 1 is 0, carry the 1, 1 and 1 is 0, carry the 1, and then we have 1. So as a positive number, this is an 8. So the that means this here, and we're looking at it saying it's the same number. This is saying it's a negative number because there's a 1 here. Well, when you apply the 2's complement, what you actually come up with 8, that would mean this is negative 8. So this number here is negative 8. And so in terms of the smallest over 4 bits, so the smallest negative, I'm at 20 seconds. Oh, so for 4 bits, it's the negative 2 to 3, so minus 8 would be the smallest. For 7 bits, it's the negative 2 to the 7, or negative 128. Sorry for rushing at the end.